Yes. So in the last class, what I was doing, uh, I think I'll just revise the last part of the class, that how to interpret this omega, which is a function of number of particles, volume, and energy, internal energy E. Okay. And since we're dealing with microcanonical ensemble, the Hamiltonian is a, if you have n number of particles, so Hamiltonian is a function of 3n position coordinates and 3n momentum coordinates. It's a multi-dimensional function. And the constraint is that your Hamiltonian has to be equal to the total energy. Okay. And if you go back and recall your Liouville's theorem, it tells you that when you talk about a system is in equilibrium, then this equilibrium distribution has to be a function of your Hamiltonian. So for microcanonical ensemble, when the system is in equilibrium, of course, then only you can think of an ensemble. Your equilibrium distribution has to be a function of your microcanonical Hamiltonian for this microcanonical ensemble H, which is a function of P and Q. P bar means all the P's. Q bar means all the Q's. And what it should be, because there's a constraint that your H has to be equal to E. So I say that this has to be proportional to something like a Dirac delta function. Dirac delta function is something like Hamiltonian minus E, and it has a value only when H is equal to E, otherwise it has no value. Of course, this value is huge, it's infinity, but this function has meaning, you'll see eventually when it is inside an integral. Okay, so this is actually 6n minus 1 dimensional hypersurface. Why? Because if I take a sphere, for example, then if I say, okay, my sphere has the radius capital E, then any particle on the surface of the sphere will have the same distance from the center of the sphere. Okay, so but the surface is what dimensional? 2-dimensional for a sphere. The sphere is 3D, the surface is 2D. So similarly, you have a 6n dimensional phase space. Then the surface of that 6n dimensional phase space, for which your Hamiltonian is equal to E, has to be 1 dimension less than 6n. So that's why it is 6n minus 1 dimensional hypersurface. You have to imagine, you cannot draw this. Okay. So this omega, it is called number of microstates, allowed microstates, with the constraint that your Hamiltonian is equal to the total energy. It is also, in other words, a measure of amount of phase space available to this system. Okay. So how would I actually calculate, compute omega? So omega, I say, okay, then omega, then this is the accessible microstate, So actually you take this, this delta function, which actually represent your hypersurface, because this is the constraint, and if you integrate this delta function over all possible values of momentum and position, okay, so you have like all the position coordinate, all the momentum coordinate, then what you get should be, maybe you have to multiply with some factor. I'll come to that. What is that factor? You will get what is known as the number of accessible microstates, and this is called omega. Okay, now you can come back in phase space. I can think of a tiny volume in phase space. Okay, so my next question is, what is the tiniest volume in phase space I can think of? Although this concept of phase space is mostly classical mechanical, because you have well-defined position and well-defined momentum, but still what is more fundamental is quantum mechanics. Okay, so if you keep on dividing the phase space into smaller and smaller volume, you can go only up to a volume which volume is equal to Planck's constant. You cannot go beyond that, because Heisenberg uncertainty principle actually restricts you to go beyond this. So the tiniest possible volume element you can have in the phase space is restricted by Heisenberg uncertainty principle, isn't it? And that is actually equal to h to the power of 3n if it is 6n dimension. Of course, if you have in 2 dimension, in 1 dimension is h, in 3 dimension is h cube for a single particle, and if you have n particle, it has to be h to the power of 3n. Okay, so this is your tiniest volume. So now we try to construct this omega. how do? You actually divide the phase space into this tiny volume, and in each tiny volume you have one microstate. So omega is number of microstate, accessible microstate. So what? So essentially what I should do, I should take delta tau, I divide it by its volume, okay, divided by volume. When delta tau equals to h to the power of 3n, you get one microstate, isn't it? So basically this will give you the number of microstates, and you add this number of microstate with the constraint that your Hamiltonian is equal to E. Here we put some kind of also uncertainty on E because of Heisenberg uncertainty principle. Okay, so your Hamiltonian can have energy E or slightly different from E, which is E naught. E naught is very small compared to E. It's like delta E. Okay, so basically this summation has to be taken for H equals to E plus E naught. Okay, that is the constraint. Which is, so H can vary only between E and E naught. E naught is very small compared to E. Of course, this delta tau is very small compared to the entire phase volume. So as a result, this sum can be approximated as an integral. Okay, so this integral and this 1 over h to the 3n will come out. Okay, this integral, of course, you can further this is a 6n dimensional integral, and then what you can do, you can further approximate this, or you can write this as that you take this hypersurface, which is 6n minus 1 dimension, okay, times this thickness of that hypersurface, which is E naught, which is E plus E naught, that thickness, okay, and then that will give, and put this delta function, because delta function gives you the hypersurface, and times the thickness, and you integrate over all possible values of position and momentum. So this will give you a prescription to calculate this omega, is a number of accessible microstates with energy E. Okay, so this is where I think I stopped, isn't it? I think I stopped here.
Yes, sir.
Yes, sir.
Yeah. So please follow the book by Mark Tuckerman, or Tuckerman, what do you want to call it, on this part. For this part, you follow this book, read this book, or go and read this book. Okay. So so your omega is given by something like thickness E naught. Okay, E naught divided by h to the power of 3n, and the integration of this delta function, which represent your 6n minus 1 dimensional hypersurface. Okay, so we'll start from here now today. But we will see that this is not enough. We will see it's not enough. Why it is not enough? Okay, what is my definition? My definition is your omega, which is a function of NVE. We are calling it something like E naught by h to the power of 3n. And then you actually integrate over all possible position and momentum. Okay. And of course, this is the hypersurface. So this is a definition, but this is not the correct definition. This is assuming that okay, you have taken care of quantum mechanics to some extent, but you assume that particles are distinguishable. We'll talk about it later in details. Okay, but in reality, if you think of say n number of electrons, they are not distinguishable, they're indistinguishable. And so if you have n number of objects, they are indistinguishable, then you know from quantum mechanics, people who have learned quantum mechanics, I think you should know that there's called fermions and bosons. Electrons are fermions. Even for bosons, you have to make a quantum correction. You should not overcount the states. Okay, so in order to so basically what you do, you introduced n factorial here, factor of n factorial. Okay, since the particles are indistinguishable, so that you don't overcount them. We'll talk about it later again. Okay. So this is my expression for omega. Then my next question is, what will be the expression for equilibrium? Can anyone tell me? Formally, it is something like 1 over omega, isn't it?
Yes, sir.
But this is a formal way of writing. If I want to write it explicitly, what should I write? You remember that because this omega, this should be a function of your Hamiltonian, and you know the function is
Dirac
delta
delta.
function. So basically, you should have a Dirac delta there, isn't it?
Yes, sir.
So actually, you should have what is known as Dirac delta here. Yes. And this factor, for example, this factor, you want to call it something, you can call it something like, what do you want to call it? Um, M tilde. This is not microscope, the factor. So, but this is not again correct because you have to multiply this with this factor. Why? Because your equilibrium distribution has to be normalized. So if you integrate this over all possible values of position and momenta, you should get 1. So what will be the answer then? Can I write it more neatly in detail? So let us write it down. This is the equilibrium distribution in microcanonical ensemble. So what will be the answer? The answer is going to be, see, omega has, so let me write down, m tilde delta h minus pq e divided by omega. What is omega? Omega is this. Omega is m tilde, your integration of so can I now basically don't have this tilde. What I have is this. Can you see this? What I have is this, your row equilibrium. You can write it like this also, doesn't matter. So essentially what you have is something like a delta function divided by integral of that delta function. Does it look familiar? You have done probability theory, some of you. It should be like this, isn't it? Think. Any probability distribution. How
Yes,
do you
sir.
write? How do you write? You write something like pi or pj,
By sum over.
sum over pi, isn't it?
Yes, sir.
So essentially this is what you are doing. Okay. So
Yes, sir.
this is your way of writing your uh, okay. So this is the way you should write. So this is your equilibrium distribution in microcanonical ensemble. In microcanonical ensemble. How many of you had chance to go through the book or have a look?
I did. Sir, I also did.
So this course, if you think that you'll read Atkins and you'll learn and you can cope up in this course, then you're mistaking. I think you understand that, no? This is an advanced level course.
Yes.
This is not Atkins, huh? Atkins kind of course. Atkins, Levine, no. You got it? That it is not. So you have to go and read. So if I have like this, then how do I define any quantity? For example, say I defined any quantity which is a function of p and q, and I take an average of that. Okay, say how do I write? I should write like this, isn't it?
Integral A row equilibrium.
Okay, and I am little lazy, so I can say it is you integrate over the whole phase. I can write like this, no? I'm not writing
Yeah.
detail. Yeah, integration over whole phase. So if you have the book with you, you can have a look at it. You have it, or I can show it in the book. I think this is exactly this. Maybe they have a different notation. Do they have a different notation? I don't remember because I was doing myself. Should be something similar, the notation. Yes. Same notation. Yes. So if you see the equation number, I'll tell you the equation number in that book. 3.2.22 in Mark Tuckerman Statistical Mechanics. Probably the page 680.
Yes, sir.
Anyone has it open on a computer or somewhere?
Yes, sir.
Maybe they have a slightly different
Yes, sir.
notation, but you understand what I'm saying. They have x for the phase integral, but essentially it is like this. Okay, so in other words, actually I can say that your omega, the number of accessible microstates, I said, na, this also, it also has a different name. You know the name. This is called microcanonical partition function. It is the number of accessible microstates. It is also known as microcanonical partition function. Okay. Now you go back and see the slides or the previous day slides. You will see that I had expressed many things in terms of this omega. For example, temperature, pressure and divided by temperature. So what is the strength of this omega? You know the Hamiltonian, you can calculate omega, and if you Hamiltonian means you know the microscopic structure of your system, you know omega, and if you know omega, take log of omega and take derivative of that log of omega with respect to some different variables, and we get thermodynamic quantities. Do you see that, all of you?
Yes, sir. Yes, sir.
So this is the strength of statistical mechanics. You're connecting to thermodynamics starting from microscopic description, and we are working in microcanonical ensemble. Eventually, we all will work in other ensemble also. And actually, all the ensembles are equivalent. You can choose your ensemble and work. Microcanonical ensemble is not very realistic because it is not going with the experiment, because you cannot set up an experiment where the system is completely isolated, isn't it? It does not exchange particles, does not exchange heat. Very difficult to set up. Even if you set it up, difficult to observe such experiment system. But it is also known as microcanonical ensemble as a mother of all ensemble. We'll see why it is the mother of all ensemble eventually. So far it is fine, because in this course I'll go little bit abstract. You understand? So you have to go and read. So if you ask me a question, I can try to explain it here, but you may not understand because you have to go back and read. And maybe when you come back next day, you'll understand by then. Okay. Please read this book by Tuckerman. It's a very, very nice book. Okay.
Okay,
Is it
sir.
clear? Yeah. It will be clearer as we progress. It will be clearer. So let us do this way. I am making it a little more abstract, but it is good because it will be quite useful. Rather than I'm writing it every time I write in the book is NVE. Okay, I can write it as omega. I just don't write n. I know there are some n number of particles. I write E and I put something like x. What is x? X can represent n, x can represent v. Actually, x represents v here. Okay, some generalized displacement coordinate you can think. Okay, it could be volume, could be area, could be length. Huh? Is this clear? This is x. Some generalized displacement coordinate. Now, if you have any question you ask me, I'm just writing at x. Is it okay if I write v as x?
Sir,
Capital X, capital X, capital X.
sir,
This is notation. Yeah.
sir, but there was an energy term too, so you have put two, combined two into one.
No,
Like
no.
V.
A I'm not writing because I'm lazy. I'm keeping E. I'm just replacing V with X, capital X.
Okay, sir. Thank you, sir.
Okay. N, you know, back of your mind, you know, there are n number of particles. Okay. Okay. I'm just making it. I'll show you why, because if I write like this, it'll be easy for me to write equations and things so far. Now, I can think of an element of an ensemble. I don't write n because it is in my back of my mind. I also don't write x. I could be even lazier. I can write like this, isn't it? Huh? Is this okay?
Yes, sir.
I know I have it in my mind that is x or v and there is n, but I'm very lazy. Take it for granted. Huh? So I have one element of an ensemble which has energy E1. Is this fine? So basically, this is an element of a microcanonical ensemble. Very simple.
So by
Element of a microcanonical ensemble with energy E1. Calling it E1. Huh? Not a problem, no?
what is meant by element?
Element means, see, ensemble is a collection of system, no? So one of the systems, one of the
Okay. One of the
imagination. Yeah, copies, one of the copies. So I can bring another copy from another ensemble, microcanonical itself, but its energy is different, E2. Okay. And I'll put them side by side in contact in such a way they can exchange heat. Heat exchange is allowed. Okay. How it is allowed? Because actually the whole thing is isolated from the rest of the world, no? And these two cannot exchange particles, but they can exchange heat. Of course, back of the mind, I know I have x1 for this, I have x2 for this, maybe I have n1 for this and n2 for this. I'm not writing. Is this fine?
Yes, sir.
Yes, sir.
Okay. So heat exchange is allowed. So now my question is, if I go to this element or this subsystem, these are two subsystems, bring them together. So I can write down this, that S1 is nothing but kb ln omega of E1. Are you fine with it? Tell me if you are fine with it.
Yes, sir.
You know the Boltzmann, Kailash, it is done in the last class. So similarly, S2, what should,
Yes,
be the,
sir.
what should be the expression for S2?
KBln of omega E2.
Omega of E2. It is obvious. Okay. Now my question is, since they can exchange heat, but the composite system is isolated from the universe, I have a constraint here also. What is the constraint? That E1 plus E2, that must be equal to some constant E. So this is a constraint. Huh? It's a constant. Huh? You understand this? I
Yes,
have two
sir.
systems. Because they can exchange energy among themselves, but they cannot exchange energy with the rest of the world. So what will happen? If one loses energy, other one gains that energy. There is no loss of the composite system, the combined system. Energy is constant, conserved. Fine? It is not very
Yes,
difficult.
sir.
Very simple, actually. Yes. Now I ask a question. Then what will be the number of microstate, accessible number of microstate microstates for the combined system? This is a question I'm asking. And we'll see how to get it. Okay. So let us try to do it. So how to do it? I draw a picture. Drawing is not very good here. So this is say E1 axis. This is E2 axis. Fine. Okay. So
Yes, sir.
I start from here. Initially, I have a system energy E1 here. The first one, and say E2 here. And I allow the system to evolve. It will evolve to go through many possible microstates, the composite system. But with a constant. What is the constant?
E1 plus E2 is equal to
Energy is
E.
constant.
Yeah, E1 plus E2 has to be equal to some constant, which is E. So actually, what is that constant on this graph? On this graph, this constant is nothing but, tell me.
Straight line
Line.
with negative slope.
On this graph, actually, if you connect these 2 points, no? Actually, you should connect these 2 points, isn't it? What do you think? You should connect these 2 points. So let us see. Not these 2 points.
2 points that lead E.
Yeah.
Yes.
So the way I've drawn, anyways, I just extend this to here and a little bit here. And this point, and then if I draw a line which is actually making 45-degree angle and going through this point, this is the actually line. So all the microstates should lie on that line. Is this clear with that constant? E1, E2,
Yes, sir.
this point. Now I move. For example, if I move, I go to, I increase E1. E1 goes here. E1 goes here. But the E2 should come down here, no?
Yes, sir.
Similarly, if I reduce E1, then E2 should increase.
In-
So basically, on that line, the line actually represents the allowed microstates for the composite or the combined system. Is this clear? Yes, it should be along the line.
Yes, sir.
Okay, so all the microstates essentially. And now I start with some initial condition and then allow my system to come to equilibrium. So what is equilibrium? For example, if I wait some amount of time, you will see that eventually the system, the composite system, will choose some microstates which are more probable. Okay. And if I construct that the density of microstates, you will see maybe after some time your system will evolve and it will go here. This is called E1 star. This is special E1 star. And if to draw it better. Oh my God. So I use a green color only. So I go here. This is, I'm calling it E1 star. And I'm just becoming very difficult. Very difficult to draw sometimes. You understand? I'm having problem in drawing. So I want to draw a vertical line actually, but I'm having problem here. Like this, for example. Okay, this point. This is E1 star and this is E2 star. This point also lies on that curve, on that line. Is this fine?
Yes, sir.
Sir, can you increase the size of this window
Yes.
little bit?
Okay. Okay, so this is E1 star and E2 star, but these are special E1, E2. Why? Because if I calculate the number of microstate, the density of microstate, I see that, okay, maybe you have some peak here, but around this, I have the highest peak. Okay. You understand? And this is specially chosen, these set of microstates. What are these specially chosen set of microstates represent? Can anyone tell me?
Equilibrium state?
Actually, that represent equilibrium state. So you remember, never forget that equilibrium state is the one which has maximum number of possible microstates. In few minutes, it will be clearer. Okay. So I go to the next slide because I can write it better. So the question I asked, what is omega of E? What is omega of E? Okay. What is the answer? Answer is, obviously I know, this omega of E has to be equal to omega of E1 times omega of E2. E2 is nothing but E minus E1. Huh? But then that is for a given value of E1, but E1 can vary with the constraint. So basically you have to integrate over E1. The constant is already there because E2 is E minus E1. Is this clear?
Yes, sir.
This is exactly the question I asked a few minutes back. And when I write this, this is the way I should write. Okay? Kailash, you follow?
Yes, sir.
And now this is integral, means I can think this is a sum. You have many terms. And this integral is not very easy to evaluate. But we will do a trick here, and which we do without knowing. And this is called that if I have an integral, sometimes I approximate, I don't know, you know. The integration has, this integral is an overlap, no? So overlap, this is like, this is overlap, no? Essentially along this line. These are the composite microstates. So I'll just take only this part, I'll not take the other part. Essentially, I'll evaluate the integral in such a way, I'll approximate that integral in such a way that I replace that integral with something, with only one term. Or in other words, I evaluate the integral following a technique called saddle point approximation. Okay. So basically, I approximate this integral with one term. What is that one term? The one term that maximizes something. What is that? You know that? So let me write down explicitly again, and it will be clearer. What is omega E1? It is exponential of, tell me, S1 E1 by KB. Is it fine?
Yes, sir.
What is the next one? Next one is S2, actually E2, no? Because E minus E1 is E2.
Yes.
So this is actually the integral. But I don't want to evaluate the whole integral. I approximate this integral with only one, what you can say, term, that is nothing but so approximate. So you can use, this is called saddle point approximation. Okay, I approximate this actually. This is approximation. So basically what I do, I just see this integral, I just take the integrand where it is very, very highly peaked and replace that integral by that integrand. Okay.
So
And if
this
I
is similar to placing a delta function, right?
it is similar to delta function, but not exactly delta function. Okay, similar to delta function. Yes, you can call. So omega e, if I write this way, what is this? So actually it tells you that if I take log of this, so kb ln omega e is equal to what?
Total
kb
entropy.
ln omega at e1 star, isn't it? Plus kb ln omega at e2 star, isn't it? In other
Yes.
words, what is this? This is what? Your SE
SE.
equal to of course this is approximately equal to, but this takes care of what? That entropy is extensive. Isn't it?
Yes, sir.
But underlying assumption is that actually you have approximated that integral with one term, and this is called saddle point approximation. But how do I know which term will contribute most? Tell me. So what I need to do, I need to extremize the exponent with respect to u1. Understand? You have to extremize the exponent. What is the exponent? Basically, what I need to do, I need to take a derivative of with respect to e1 of what? And what is the answer? Remember, your
Should have to be zero.
yeah, there has to be 0, of course. And your e is e1 plus e2, or e1 is e minus e2. So del e1 is fine. So what is the first term then? Kb, you just multiply both sides by kb, doesn't matter. So first term is going to be del s e1 into del e1. Of course, here I just what I have forgotten, I put it there. I put that thing x1. Remember, x1 is like the volume v1, plus at x2. What is the next step? Next step is or in other words, I can write it again. Let me write down one more time. And this is the condition of equilibrium, because equilibrium is the one where you have the maximum number of microstates. So basically I look at where this integral is peaked around. and I replace that integration by that integrand. And this is a condition for equilibrium. Is this clear? This is a condition for equilibrium.
Thermal equilibrium.
Thermal equilibrium.
Yes. And the next thing is, this is condition for thermal equilibrium. And this equilibrium is thermal. That I write in bracket. Because this is equal to, it is consistent with the thermodynamics if I put 1 over T. No? This 1 over T is called empirical temperature.
Why empirical?
Just not the T, 1 over T. This is, the people call it empirical temperature because it has to be equal to something which is like temperature, but dimensional analysis tell you it has to be 1 over T. Okay.
Okay. 1 by T.
Yeah. It doesn't matter if you forget it, it's fine. But what is important that del S del E equal to 1 over T. So this is one way of defining temperature, isn't it? And you can construct S from omega, taking kb ln omega, and take a derivative of that with respect to E. And this is done also in the last class, isn't it?
Yes, sir.
Yes, sir.
In a different way, but I'm doing it in a different way. But this is how you actually define thermal equilibrium. But while doing so, you have done something. We had done third law heuristically. Today I have done another law. What is this law?
Second law.
No.
This
This is zeroth law.
Zeroth
This
law.
is zeroth law. Dynamics. And while doing so, see what I have done. I have extremized what is known as entropy. The exponent is nothing but entropy, no? So basically, it is very important that all of you know and remember that your system evolves to a state where the entropy is maximum. Did you know about it? I think you knew from thermodynamics, maybe in different way. It will come. Okay. So basically, an equilibrium state is something where the entropy is maximized. Are you convinced?
Yes, sir.
Yes, sir.
So basically, when you have a process where entropy is increasing, you're getting spontaneous. So basically, the system is trying to find out an equilibrium. It's going to it's trying to equilibrate, trying to maximize its all possible microstates. It's like that. Anyway. So this is zeroth law. Okay. So now let us try to.
If you had not done that subtle approximation,
Yes.
had the results been different?
No,
Or
there
what?
will be corrections, but these are very negligibly small. Actually, you'll see that number of microstates for equilibrium state is huge compared to other states. Those states are preferred.
Okay.
Those states are preferred. Yes.
So
Hello.
that
These are
approximation
these
is just for calculation.
Yeah, this is a very good question. Yeah, because if you stretch it further, you go to this philosophical part of statistical mechanics, aspect of statistical
Hello.
mechanics.
Sir,
Yes, tell me.
sir, the peak that you have drawn, the equilibrium has the largest microstate. So isn't
Yes.
it not like contrary to the equal a priori principle that we have used in for the
No, it is not
microcanonical ensemble?
not contrary, because it is a composite system. No? This is how I did. How I did.
Okay,
It is not.
E1 plus
It is
E2
not. It is not. It is
minus.
not a probability. It is not a probability.
Oh,
It is not the probability. Your omega is peaked around that. Omega is number of microstates. All the microstates are equally probable, but their density is not uniform. Get it right. What's your name?
Sebastian.
Yeah. Again, I repeat. All the microstates are equally probable. Okay. But some microstates, all the microstates are equally probable. But in equilibrium, when you go to equilibrium, you have special microstates chosen for equilibrium, which has the highest density. So along that line, the line I draw, each point is equally probable, but the density of points is not equal. You have not uniform density, but each is equally probable. The density is not equal. Maybe you can think about it and come back.
Yes, sir.
It is not violating a priori hypothesis. A priori hypothesis says that okay, all the microstates are equally probable. Okay, all the microstates are equally probable.
Yes, sir. But so here the plot is the density, basically the density.
Basically, the density actually. It is basically the joint number of states.
Okay, sir.
So the joint number of states is extremely large at equilibrium energies. Equilibrium energies. Okay, that E1 star and E2 star, they are extremely large. Okay.
Hello, sir.
But if I and a priori hypothesis is what? If I give you energy E1, then all the microstates are equally probable. But here I'm changing energy. You understand?
Basically, the microstates are scattered. So
Yeah. So I'm changing the with given energy E1, all the microstates are equally probable. Even with given energy E1 star, all the microstates equally probable. But microstate that corresponds to E1 star, they are more probable than microstates that correspond to E1. Is this clear?
yes, sir. Now I got it. Yes, sir.
Okay. You understand what I'm saying?
Yes, sir.
Yeah.
Got it.
So some energies are preferred, and those energies are equilibrium energies. And for that, number of microstates are. If you have this energy, then you'll have more number of microstates belonging to that energy. Yes. Someone had a question.
Yeah, sir. Actually, I want to say that can we say that this is the microstate which has a more possible microstate? That is why this is more probable.
Yeah, but I just explained now. So with that equilibrium energy, if you have energy given E1, you just please mute yourself. E1.
Okay.
If you have given energy is E1. With that E1 energy, all the states are equally probable. All the states that give rise to E1, they are equally probable. But maybe with E1, you have say 1 billion states. You understand? But with E1 star, here also all the microstates are equally probable, but you have then 100 billion states. You got my point? All of you?
Yes, sir, exactly.
You understand, no? Try
Yes,
to
sir.
visualize this, okay? There are special energies which are equilibrium energies, and for those equilibrium energies, number of microstates is huge, but all the microstates are equally probable for that particular energy.
That hypothesis was for microcanonical ensemble.
Yes.
Yeah.
So that hypothesis is for a given energy. Even for given E1 star, all the microstates are equally probable, but they are more in number. You understand? They are more in number.
Yes, sir. Got it.
They have say 100 billion. For any non-equilibrium, not equilibrium state, they are say 1 billion, half billion, or something like that. So basically, this integral has 1 billion, 100 billion plus half billion, 1 billion. So I don't take those. I take the 100 billion one. I approximate that with that integrand, and then that is what is known as extremizing your entropy, maximizing your entropy. Okay? Get these things clear because it will be very useful throughout your life. Okay, so after doing first law, let us try if I can do second law of thermodynamics. You can do. I'm sure it is not taught this way in 408. Kailash?
Definitely, sir.
Yes.
Obviously.
So second law of thermodynamics, sorry, not second law, first law of thermodynamics, second law I'll do later. So let us see whether you can get this. Uh, so changing the coordinates reversibly by this. Okay. So I have coordinate x, and I change this coordinate x to x plus very small one delta x and do it reversibly. You got it? So I can take a gas inside a piston. I change the I replace the piston by slight amount. So I change the volume, isn't it? It's like that.
Yes, sir.
Good, very good. So then my entropy, here I am writing it as function of E and X. Okay. So there will be some work done. No? This work done, some notation I am following. I can write it something like a generalized force times this displacement. You understand, no? Like PdV, like JdX. Is the work done? Is this clear? It is PdV essentially. I hope you're following.
Yes, sir.
Yes, sir.
Like PdV, I'm just don't like it. Don't want to write it V. I write it X. I don't want to write V. So any work done is force time displacement, isn't it? Pressure is force divided by area. So and volume. So force divided by area into volume is force times displacement, isn't it? Force
Yes,
time
sir.
length.
Yes, sir.
Okay. So this is your entropy. It's like this. So then my entropy has now changed from S to S plus S E plus sorry X plus I have to write. You can follow this, but the change. So what is the
Yes,
change
sir.
in entropy? Change in entropy.
Del S del E into dE plus
I will do that later, but let me write down here using this notation.
S of E plus J del X. X plus del X minus S.
Okay, and this one is equal to I do something like Taylor expansion, and I go up to first order. I don't go beyond first order. If I do this, I'll have plus del S del E, of course some you have to call it some X J into delta X plus del S del X because delta X is very small, so I don't take any second order term. Is this clear what I have done?
Yes, sir.
Can I cancel this too?
Yes, sir.
So what I have here is delta S is equal to the way it have written, yes. And since I was in equilibrium, for example, and I do a small reversible change, system will come back to equilibrium, try to come back to equilibrium, no? So what will happen to this change in entropy? Delta S, because this change will occur simultaneously. So the system was not in equilibrium, for example, then the change will occur simultaneously and it will go to a more probable state. So as a result, this variation in delta S has to be equal to 0. Okay, because no, I think so. If it is non-zero, then it will go. It is going to more probable state. But if it is already in the most probable state, then it is 0. Is this clear?
Yes,
Sir,
sir.
could you make
Yes,
it a little?
that is the right step. What I am saying that if your system is in already in equilibrium, then your delta S has to be 0. If you try to displace the system and by a very little external force, the system will try to resist because it is already in equilibrium, isn't it? So as a
Yes.
result, the change in it will adjust with itself in such a way that your change in entropy is 0. Okay, the system is already in equilibrium, no?
And this is true because the process is reversible and so very, very slow.
Of course, yes.
Quasi-static process is going on.
Yeah. Okay, so if delta S is 0, then what I get here? What I get here is, you remember what is del S del E? Achha, let me write down del S.
1 over temperature.
So
This is the condition, no? So what is this del S del E?
1 by T.
1 over temperature.
Basically, I can write J by T minus J by T is equal to Are you fine with it? It should be, no? Yeah, you understand, no? Because
Yes, sir.
this thing is 1 over T, no? This thing is 1 over T. This minus J by T equal to del S del X at E. Okay? This is fine.
Yes.
Yeah,
Yes, sir.
very simple thing. But again, you recall that your entropy is a function of E and X, isn't it? So an exact differential of entropy will be what?
Del S del E dE plus del S del X dx.
Which basically means what? Del S del E, you know what is that?
1 over temperature.
And what is del S del X?
J over temperature.
By T.
P by T.
So basically, it is nothing but what is this?
First law.
First
First
law of
law of
thermodynamics.
thermodynamics.
Yeah. You can take this minus J dx. Any convention is fine. Okay.
Yes, sir.
Sir, one curious question.
Yes.
They always say that the laws of thermodynamics can never be derived.
Yeah. So
What
you
is that
cannot
then?
derive, of course. We are not deriving, but we are
So
saying
what is
showing it
that?
is consistent with thermodynamics. To put it that way. You are not deriving. See, because you're showing it is consistent with thermodynamics. Because when you put del S del equal to 1 over T, you just put it because it is consistent with thermodynamics, isn't it? And that you use here. So you're not deriving. You are just
Yes.
showing
Right.
that your formulation, starting from microscopic description, is consistent with thermodynamics. Okay.
Yes, sir.
Okay. Now, if I can show first law, second law, I should also be able to. I should also be able to show second law of thermodynamics. Okay. So if I write like this, okay, I just want to call it 1 1, consistent with the book. Is this clear? Because this is equilibrium. So any equilibrium state is preferred over any non-equilibrium state, isn't it? So
Yes, sir.
equilibrium has more number of accessible, has a large number of accessible states than any
Hello, sir.
other state or than any uh, initial any starting point rather. Yes.
So sorry to interrupt, but we have one lecture now.
We'll finish in 5 minutes. Okay.
Okay,
We
sir.
will. Yeah. So this is fine. Which course is this?
Sir, biopolymers.
You can leave if you want, because we'll finish in. So essentially, also I can write that the change in entropy, that this entropy change, entropy of the equilibrium state minus the entropy of the starting state. What will happen to this? Can anyone tell me what is this? This has to be equal to greater than equal to 0. Fine. But this is equilibrium and this is the starting point. I start the state system is in some arbitrary state, and then I system evolves to equilibrium. The entropy change should be what?
Greater
Greater
than
than
0.
0. And you know that if I write down del S, what is that? It is ds1 d1 x1 minus, because here the change in del S is not because of change in x, but because of change in what? E. Huh? Is this clear?
Yes, sir.
Of course. And this is equal to and this basically tells you that heat flows from hot to cool body. And this is nothing but second law, isn't it?
Yes, sir.
And we will stop here today. Because delta is arbitrary, no, it could be plus or minus. Of course, if it is plus, then this quantity has to be plus. This is minus, this quantity has to be minus. Okay. So basically, the two temperatures should be like, you understand what I'm saying? One You, so one has to be greater than the other. So basically, heat will flow from cold, hot
Yes,
to
sir.
cold body. I'll stop here because I think it is already quite heavy. So I hope that you are following the course. How many of you are following the course? Because I think many people are dropping out because it is
Yes,
very
sir.
abstract course maybe. I don't know. But some people are following, I'm sure. Kailash, you are following the course?
Yes, sir.
Deepak,
Absolutely.
Deepak.
In fact, I am enjoying this course.
Yeah, because see, in my course you learn something. So learning is more important than getting marks. You will get marks, of course, getting grades. So try to learn. And others, they're following the Anish and others.
Yes, sir.
Yes.
Yeah. Okay. So who are there in the okay, who are there among 17? Let me see who are there. I don't check actually.
And the book you recommended, the language of this book is also very nice.
Yeah. Nashit is there, I
Very
know.
good.
Yes.
Yeah. Bharati. Okay. So anyway, good. So this course is going to be like this, and hope you're enjoying. Okay. So we'll meet again on Thursday. Okay.
Thank you,
Bye
sir.
bye. Yeah.
Thank you,
Thank
sir.
you.
Thank you, sir.